Okay, get started. So last time we looked at the approximation where the universe consisted only of a single thing. So now we're looking for realistic universes where there are multiple components. And solving the Ryden equation and the acceleration equation, these multi-component universes numerically ends up giving us a good description of the history of the universe from the Big Bang until today. So we'll recall that the Friedmann equation told us that h of t squared, which is a squared over a squared, is 8 pi g Newton over 3 c squared epsilon of t minus kappa c squared over r squared a squared. And here, epsilon of t, the energy density, is the sum of the energy density of various things in the universe with different equation state parameters W. And in addition, we have a relation that says the pressure of a thing is the energy density of the thing times the equation state parameter. So let's divide this equation by the critical energy density. Critical energy density is 3c squared over 8 pi g Newton, h of t squared. So when we do this, we get 1 is omega of t minus kappa c squared over r squared a squared h squared. So omega is the ratio between the energy density and the critical energy density. So in particular, today, omega 0 minus 1 is times h0 squared over c squared. This is equal to kappa over r squared. So in particular, the deviation between omega 0 and 1 tells us a sign of kappa. Okay? So if the universe is flat, kappa equals 0, this implies omega 0 is 1. Okay? Using these definitions, yeah?
Should it be a times h of t squared?
Here,
No, it's called energy density.
it is h of t squared.
Times it must be like.
Yes, it should be. Thank you. Usually the notes are correct. Transcription errors happen on the board. So we can use these definitions to rearrange things to look like h of t squared is 8 pi g Newton over 3c squared epsilon of t minus omega 0 minus 1 a of t squared h0 squared. So we just subbed in for kappa over r squared into the Friedmann equation we read earlier. Okay? So the ratio between h of t squared and h0 squared is epsilon of t over epsilon critical today plus 1 minus omega 0 over a of t squared. Again, just rearranging terms. So here, epsilon critical 0 is 3c squared over 8 pi g Newton h0 squared. Okay? So we've done a bit of algebraic manipulation in order to re-express things in this form. So now, we know that epsilon t breaks up into various components. There is epsilon associated radiation over a to the fourth, plus epsilon associated matter over a cubed, plus the epsilon associated Scott functional constant. And this expression here is epsilon of t. So that plugs into the numerator. And each of these terms have different equation state parameters. W is equal to 1/3, W is equal to 0, W is equal to -1. Yeah?
Can you just increase the font of the
Okay, I'll increase the font. So we have, we've got these different components, and they have different behavior with the scale factor. So the matter, it dilutes as the volume, that's 1 over a cubed. The radiation dilutes as the volume, plus it redshifts, it stretches as the universe expands. That's 1 over a to the fourth. The cosmological constant remains constant. Energy density there remains the same, irrespective of the expansion of the universe. So, plugging this into here, we can rewrite h of t squared over h0 squared is omega r0 over a to the fourth plus omega m0 over a cubed plus omega n to 0 plus 1 minus omega 0 over a squared, where omega I0 is epsilon I0 over epsilon C0, and omega 0 is the sum. Omega radiation 0 plus omega matter 0 plus omega lambda 0. Okay, so you'll notice that epsilon lambda 0 is epsilon lambda, but omega lambda 0 is not omega lambda because you're dividing by the critical energy density, which is a function of time. Okay, so the data we have is consistent with omega 0 equals 1, but the error bars are such that we don't actually know whether it's slightly bigger than 1 or slightly less than 1. That's also allowed by data. Okay, it's very close to 1, however. Okay, so let's multiply this equation by a squared and take the square root. When we do this, we have h0 inverse, a dot. So h is a dot over a. So we multiply it by a squared. This is omega r0 over a squared plus omega m0 over a plus omega lambda 0 a squared plus 1 minus omega 0. So we multiply by a squared, and then we take the square root. So we take the bottom expression and integrate. When we do that, we find that h0 times t is the integral from 0 to a dA over omega r0 over a squared plus omega n0 over a plus omega lambda 0 a squared plus 1 minus omega 0. So, we can figure out what omega r0 is, omega m0, omega lambda 0 from measurement. We can plug into this expression and then just integrate in order to get the behavior of the time. The problem is that when all of these terms, the numerator, are non-zero, the integral doesn't have a nice analytic expression. Okay? So there's no nice analytic form, but we can solve numerically. But the good thing is that in most of the universe's history, we need only look at one or two terms. So last week, we studied what happens when we only look at one term. So this week, we'll focus on basically this equation when we look at two terms, for the most part. Okay. So I'll remind you that the scale factors in, so the terms describing the radiation and the matter, they're equal when the scale factor is about 2.8 times 10 to the minus 4, and matter and lambda are equal when the scale factor is about 0.75. So, for example, when ARM is much, much less than A, which is much, much less than AM lambda, it's sufficient to look at matter only. Similarly, when A is much, much smaller than ARM, we look at radiation only. And when A is much, much bigger than AM lambda, we look at lambda. So right now, the contribution from the cosmological constant is about 0.7. The contribution from matter is about 0.3. So it's not the case that one is much bigger than the other. So right now, we look at both matter and cosmological constant in order to describe the behavior of the universe. Okay? But we're moving towards a phase when only cosmological constant will matter. So one of the questions you might ask is, why is it that we happen to be living at a period in the history of the universe when two terms are important, whereas for most of the history of the universe, only one term is important? This question is called the coincidence problem. Why are we happening to live at this coincident time? There's no good answer. We just happen to live where we live is one answer, but that may or may not be satisfying. Incidentally, if we lived in a universe that was a typical universe, we'd largely be living in a time that only the cosmological constant is dominant. Because that's what happens for most of the history of the universe. Most of the lifetime of the universe, only the cosmological constant term dominates. So if we were doing cosmology in a universe with only the cosmological constant term dominating, the universe is exponentially expanding, as we saw last week. So eventually, the only things which are within the horizon are things which were gravitationally bound, the reverse supercluster, for instance. So if we were happily living in such a universe, we wouldn't really have much cosmological data. We'd only have data related to the galaxies that we can see. Those galaxies are gravitationally bound to us. Nothing too interesting is happening with them. It's only because we can see beyond things which we're gravitationally bound to that we have cosmological data. So it's a golden age of cosmology in two senses. It's a golden age of cosmology in the sense that we now have satellites up there taking measurements, and we're using those measurements in order to study cosmological structure. But it's also a golden age of cosmology in the sense we happen to live at this coincident period when we can have data at all. Okay. So let's look at our first multi-component universe. Look at matter plus curvature. So if it's matter only, we saw that A of t was t over t0 to the 2/3 power. The universe expands forever. And we saw the temperature is proportional to the inverse of the scale factor, so as it's expanding, it's cooling down. And it cools to the so-called big chill. And because it cools, there may or may not be a heat death in the universe. So it's traditional in the cosmology course to quote T.S. Eliot at this point. This is the way the world ends, not with a bang, but with a whimper. So we have in this universe matter and curvature. Omega r0 equals 0. Omega lambda 0 equals 0. And omega m0 we'll call omega 0. And so the Riemann equation looks like h of t squared over h0 squared is omega 0 over a cubed plus 1 minus omega 0 over a squared. So this is the matter piece, and this is the curvature piece. Okay, so we noticed that with a matter-only universe, the universe expands forever. Here, that may or may not be the case. So let's suppose the expansion is not infinite. So there's some time at which the expansion stops. If this is true, then that means A dot has to equal 0, because we've maximized A. So this implies that H equals 0 at some special time. At that time, the left-hand side vanishes, and we have 0 equals omega 0. Let's multiply everything by A squared, A maximum, plus 1 minus omega 0. So this implies that A max is omega 0 over omega 0 minus 1. Okay? So in order for these two terms to exactly cancel, this term needs to be opposite sign of that term. So this tells us that omega 0 is bigger than 1. So this means, equivalently, kappa is plus 1. Okay? So if kappa is plus 1, we live in a universe with matter and curvature, then the expansion has to stop at some point. In the Riemann equation, only h squared appears. So after we get the maximum, the universe undergoes a time reversal of what it did in order to achieve the maximum. So the scale factor essentially does this. It starts out at 0, it does something in the middle, which we don't know, it reaches a maximum, a max there, it repeats whatever it did, and eventually it shrinks to 0 size. So we need to figure out what it does in the middle. Whatever it does, it's a time reversal of what it did to get it. So the universe, in the end, collapses to zero size, zero scale factor, and we call this A equals 0 at late times the Big Crunch. The universe begins in the Big Bang, it ends in the Big Crunch. And because, let's say, we reach the maximum at time t max, the total lifetime of the universe is twice t max. So what happens is during the contracting phase, things are expanding right now, so galaxies are redshifted. That's what we see. During the contracting phase, galaxies will be blue shifted. Okay? So, what we see is CMB today. The CMB is the microwave, it's a cosmic microwave background. So as this proceeds, we'll see a cosmic infrared background. And eventually we'll see a cosmic visible background, which should be pretty cool. We look very far out and we'll see colors in the sky. Then we see a cosmic ultraviolet background. And then eventually, a cosmic X-ray background and a cosmic gamma ray background as the universe is contracting. Okay, so we looked at the case where kappa is equal to +1. What happens if kappa equals -1? So if kappa is -1, then this tells us omega 0 is less than 1. And the right-hand side of the Friedmann equation is equal to omega 0 over a cubed plus 1 minus omega 0 over a squared. So omega 0 is less than 1, so the numerator here is positive. Both of these terms are positive, which tells us that the expansion keeps going. And we end up with big children now. Okay. So in such a universe, at late times, you've got a term which so if kappa is negative, you've got a term which grows like 1 over a cubed at late times, and a term which grows like 1 over a squared at late times. So a is getting bigger and bigger and bigger. So this term dies faster than this term. Okay? So in such a universe, the second term will dominate. So we have a dot over a0 equals square root 1 minus omega 0. So I've multiplied this equation by a squared and taken the square root. So this tells us that a of t is h0 square root 1 minus omega 0 times t at late times. So the universe grows linearly, which is what we saw for curvature previously. So depending upon the sign, we have different possibilities for the final end state of the universe. We have, if omega 0 is less than 1, this corresponds to kappa is -1. At early times, when matter dominates, you have t to the 2/3, and this ends up going to something which is linear in t, corresponding to this case here. If omega 0 equals 1, the curvature term drops out, kappa is equal to 0, and a is proportional to t to the 2/3. And if omega 0 is bigger than 1, we have kappa equals 1, and the endpoint is a crunch. And we have the expression H0t is the integral from 0 to a, dA over omega 0 over a plus 1 minus omega 0, the 1/2. Okay, so let's see what the solution to this equation is. Let's do that integral. Okay, so the claim is that for omega 0 bigger than 1, so in other words, corresponding to the case kappa equals +1, the solution is described parametrically as a of theta is 1/2 omega 0 over omega 0 minus 1, 1 minus cosine of theta, and t of theta is 1 over 2 h0, omega 0 over omega 0 minus 1 to the 3/2 power, theta minus sine theta. So you plug t and a into this expression and you integrate, you'll find the two sides agree for any value of theta. So, the big crunch corresponds to theta is 2 pi. So, if we plug in 2 pi into t of theta, t of 2 pi is pi over h0, omega 0 over omega 0 minus 1 to the 3/2. So this is a lifetime of a universe that has a big crunch. Yeah.
What is omega?
Theta is just an angular variable. It goes from 0 to 2 pi, and it's just a parametric variable that lets us express both a and t in terms of that variable. It's so instead of writing down a function a of t, I'm writing down an implicit function a of theta, an implicit function t of theta. Okay. So when you have an integral equation of this form, typically the answer is best written in a parametric way. You can take, in order to find a of t, what you do is you take the inverse of this to get theta of t, and you plug it into here. It's just much messier. Okay? If omega 0 is less than 1, we have a different parametric form. A of eta is 1/2 omega 0 over 1 minus omega 0 cosh eta minus 1. And t of eta is 1 over 2 h0 omega 0, 1 minus omega 0 to the 3/2 sinh eta minus eta. So whereas before, theta went from 0 to 2 pi, eta goes from 0 to infinity. So let's plot what this looks like. So that's A, the scale factor. That's H0, T minus T0. So I'm picking these coordinates because H0 has units of inverse time. So this variable here is dimensionless, similarly the scale factor is dimensionless. So if omega 0 is equal to 1, the universe just expands t to the 2/3 power. So at this curve here, and the expansion keeps going. Color chalk. If omega is less than 1, chalk's useless. This one's better. Also useless. Up here, omega 0 would say 0.9. It looks something like that. It keeps expanding as well. It expands, the scale factor at late times increases faster than the scale factor in a flat universe. But these are very close to each other at early times. So maybe I'll draw this slightly differently. Like that. So very close to each other. These curves look like they're almost on top of each other, so we can't distinguish them based on data. And if omega is, say, 1.1, slightly bigger, it crunches. So if you just have measurements down here, these are hard to distinguish. So that's what I mean when I say data can't resolve the different possibilities with a flatness parameter. Okay? So right now we don't know whether kappa is +1, -1, or 0, because our resolution isn't good enough to discriminate between these curves at early times. Okay, so that's our first universe with multiple components. Matter and curvature in this universe. Now I'll move on to the second one, matter and cosmological constant. So who's working with a two-component universe for the moment. We have kappa equals 0, working on a flat universe. We'll have omega m0, we'll call that omega, we'll call this, so omega 0, omega m0 plus omega lambda 0 is omega 0, and omega lambda 0 flat because kappa equals 0. So omega lambda 0 is 1 minus omega m0. Okay, so if Freeman equation is h squared over h0 squared is omega m0 over a cubed plus omega lambda 0 omega 1 minus omega m0. So this term here is always positive. And this term is positive if omega m0 is less than 1 and negative otherwise. Okay, so a flat universe with omega m0 less than 1 means this term is positive and the second term is positive. That universe keeps expanding. Okay, so our universe right now has omega m0 is 0.3, omega lambda 0 is about 0.7. So that's an example of a universe that will keep expanding forever. Okay. So flat universe with omega m0 less than 1, this guy expands forever, and as a result, it's an example of a big shell universe. Okay, suppose, on the other hand, omega m0 was bigger than 1. Then omega lambda 0 is 1 minus omega m0, smaller than 1. Smaller than 0. So, we have two terms on the right-hand side. We have opposite signs as a result. So omega m0 over a cubed, for whatever value omega m0 is, however positive it happens to be, it eventually becomes smaller than the other term. Because a is getting bigger, this term is getting much, much smaller. So a is an denominator. Okay, so the negative side eventually wins, and eventually 0 is equal to omega m0 over a max cubed plus 1 minus omega m0, which implies then the universe again achieves a maximum, and a max is omega m0, 1 minus omega m0 to the 1/3. So this universe is infinite in spatial extent because the sections are flat, but it's finite in time. Okay, so it's an infinite universe in space. And it's finite in time. It's eventually able to plunge. So we can plug in, and we find that h0t in this universe is the interval from 0 to a, dA, over omega m0 over a, plus 1 minus omega m0 a squared, square root. So this interval you can look up. If you do this interval, you'll get 2 over 3 square root omega m0 minus 1, inverse sine a over a max to the 3/2 power. So you can solve for when the crunch happens, and when you do that, you'll find that the time of the crunch is twice the time of A max, which is 2 pi over 3 root omega m0 minus 1 h0. Okay, so that's following this universe notes. So again, we can plot what happens. So we plot the scale factor A against A0 t minus Q0 if omega m0 is equal to 1. This is what happens if omega m0 is less than 1, and if omega m0 is bigger than 1, so this is omega m0. So a negative cosmological constant here provides so a negative cosmological constant provides an attractive force that closes the universe quickly. A positive cosmological constant provides a repulsive force that drives the universe apart exponentially at late times. And in the middle, we have just t to the 2/3 type behavior again. So the big crunch with a negative cosmological constant is very, very fast. The universe expands for a bit and then crunches very quickly compared to these other universes. So, for example, for omega m0 is 1.1, the time for the crunch is about 7 inverse Hubble times. Okay, so if we were in such a universe, we'd be close. We would be close to finished, but we would be a significant part of the way to being finished. So roughly speaking, the age of the universe is 1 over h inverse. So this is only 7 times the present age of the universe when we would crunch in such a case. So we're not in such a universe. We're in a universe which more resembles this one. So we'll pick up again on Thursday with more about this matter plus lambda case, and then we'll explore the other universes with matter radiation and other stuff as well. Okay.